Welcome to the 8th episode of the Quantum Physics series. Today we're exploring a pivotal moment in physics history, the Ultraviolet Catastrophe. First, let's talk about blackbody radiation. Imagine an idealized object that absorbs all light and radiation that falls onto it. This object, called a black body, also emits light when heated, just like an ember. This way, we know that any light we detect coming from it has been emitted rather than reflected. To determine the energy emitted by a black body, classical physics first used the Rayleigh-Jeans law, which assumed that energy could be emitted at any frequency continuously. According to this prediction, the energy emitted should increase continuously with frequency. This means that at higher frequencies, particularly in the ultraviolet range, the energy emitted would grow without bound, leading to an infinite amount of energy. This discrepancy with reality is known as the ultraviolet catastrophe. To accurately describe the energy emitted in the form of high-frequency radiation, William Wien proposed a new law. However, it didn't quite match observations for low-frequency radiation. In 1900, physicist Max Planck proposed a groundbreaking idea. He suggested that energy is not emitted continuously, but in discrete packets called quanta. This concept of quantization means that energy can only exist in specific, fixed amounts. In classical physics, the idea that energy can vary continuously allows for unlimited combinations of frequencies. However, when energy is quantized, each packet of energy has a minimum size that must be satisfied to produce light. Since lower frequency waves carry less energy, they are easier to produce, so many will be emitted. In contrast, higher frequency waves require a greater amount of energy just for one quantum, one discrete packet of light, to be produced. Considering light as quantized was revolutionary because it accurately described energy behavior at small scales, like in atoms, which later helped Niels Bohr formulate his atomic model. Even though Planck thought his idea was just a cool way to align theory with practice, it led to the development of quantum mechanics, transforming our understanding of physics and enabling technologies like semiconductors and lasers, proving that this interpretation was correct. In summary, the ultraviolet catastrophe challenged classical physics and led to the birth of quantum mechanics through Planck's idea of quantized energy. This discovery paved the way for many modern technologies, such as LEDs, solar cells, and quantum computers. Thanks to Max Planck's idea, the quantum revolution had begun. Thank you for joining us. Stay curious and keep exploring the wonders of science.